Hi everyone. I'm not going to say this is part two because it really isn't. It's just a different version of the ladder problem, your favorite. On the previous one, if you haven't seen the other one, I think people say I'll leave a link in the description. Well, I'll leave a link so you can watch it uh, if you haven't seen how we got the distance, right? In this one, we wanted to find the maximum distance before this kid uh, slips. We don't want him to slip. And for this one, I'm just going to read it. It says a 21.7 kilogram toddler climbs up a uniform 91 Newton ladder. The upper end of the ladder rests on a frictionless wall. The bottom of the ladder rests on a floor with a rough surface where the coefficient of static friction is 0.31. The angle between the horizontal and the ladder is 60 degrees. Find the force of friction as the toddler climbs the maximum distance before the ladder slips. Assume the ladder will not fall. The acceleration of gravity is 9.8 meters per second squared. Okay, so we have the same situation as the other one. As I said, this is the other one. We found the maximum distance. And to make this a bit more time efficient, I wrote the given. Everything before the force of friction, this is force of friction, was given within the text, and this is part of the drawing, okay? This is the weight of the ladder. The difference is now we don't have a massless ladder as we did in the previous version of this problem. So now we have a ladder which has mass, and that seems to be the case in the real world, right? Things do have mass. Ladders have mass. So now we're going to have a ladder with mass. So the way we can model this problem is with a system in static equilibrium, and we know that we have two conditions for that to happen. So let's write them down. A system is in static equilibrium. So let's write static equilibrium, or just equilibrium, right? Not even static. So I'm just going to say equilibrium. This one is in static equilibrium, but these conditions, they don't have to be, these conditions don't apply only for static, only for static systems. The ones we're going to use right now are the sum of the forces. Let's try it again. Let's try that again. The sum of the forces is equal to 0, and the sum of the torques is equal to 0. Okay. And what we have to do for this one is we have to start with the forces. And when we use forces, we have a free body diagram. I'm going to move it. No, I'm just going to leave it here. And this one represents the 91 newtons. In this red arrow is the weight of the toddler. Now this distance d right here, you can see this is not 2.2 meters because the ladder is 4.1. So the midpoint would be 2.05. So the kid is past the center of mass because it's uniform, right? The center of gravity is here. I try to get the middle, maybe I didn't, but just pretend this is the middle center of gravity for the ladder. So this vector right here is the weight of the kid, mg. So this is the vector force for the weight of the kid. This is a vector force for the 91 newtons of the ladder's weight at the center of gravity. And then we have to list all the forces. We have the force of the wall here. It's in contact. So I will add a vector which represents the force of the wall. We're going to call it F sub W, force of wall. Like this. Let me use blue. The force of the wall. And then we have a normal force here, right, which is acting opposite in direction but equal to these two combined. So we have a normal force. The magnitudes are not going to be drawn to scale, right? Although I should, I'm not going to, but just know that This is equal and opposite, equal in magnitude, opposite in direction as these two added. If I add these two tip to tail, I'm probably going to get something longer than this. So okay, I guess I'll make it a little bit longer. Just like that. And this is the normal force. I should keep red for consistency. This is the normal force. And we'll paint this red, force of the wall. Okay, and we have everything we need, right? These are the forces. Oh, wait. We're missing the one that's acting equal and opposite to the force of the wall, which is in this direction, it would be the friction, right? So we have a rough surface. So this is the friction. This is the force that is keeping the wall from falling. You can, I don't remember which class period I did this for, but I was leaning against the board and I said, what's keeping me from falling? What if I didn't have my shoes? And it was friction, okay? So we'll add the force of friction. Let me make this a little bit longer. There you go. The force of friction, and it has to be equal and opposite to the force of the wall. Let me change to red. There you go. About the same. Normally I would add it here, but I'm not going to do that. You'll see why. So let's leave it here. And this is the force of friction. Lowercase f. There you go. Now we have all forces. We can start working with the first condition for equilibrium, which is the sum of the forces is equal to 0. Net force acting in the system is 0. So we'll start with the sum of the forces acting on the x direction. That'll be the force of the wall and the force of friction. I'm going to make to the right positive, so it'll be force of friction minus the force of the wall is equal to 0. If I move the force of the wall to the right side, I know that the force of friction and the force of the wall are equal and opposite. That is it for my x direction. Now for the y is a little bit different because now I have not 2 but 3 forces, right? So up is positive for this one, so I have the normal force minus the weight of the ladder. I'm going to say WL as I have it over here, minus mg, that is the weight of the toddler, and that is equal to 0. If I move weight of the ladder and weight of the toddler to the right, I'm going to get that the normal force is equal to the weight of the ladder plus the weight of the toddler, mass times acceleration due to gravity. And that is it for the sum of the forces. Now we have to talk about the torques. We have 3 acting on this system. Okay, and to identify, let's identify the pivot point. That would be here, as we discussed during class in the review. Here's the pivot point, right? And I'm going to start with this force, the force of the wall, right? Because I have a force acting on the ladder. If for some reason, right, let's say we had an apparatus here that would somehow apply a greater force, the ladder would do this, right? It would follow this, kind of like this motion. And so I'm just going to state what the torques are. So we're going to have one torque. Let's use green for torque, right? It'll be one here. Oh, oops. One torque here. We're going to call this torque 1. And then, so this is a pivot point, right? We have a torque over here at the center of mass, center of gravity, because the pivot point is no longer the center of gravity. So we have torque 2 because of the weight of the ladder, plus this one over here, the weight of the kid. Torque 3. So 3 different torques. Okay, now let's come up with their equations, and then we'll continue the sum of the torques over here. Let's start with this one, the torque being applied here at the force of the wall, right? I I know the length of the ladder is 4.1. I think it's gonna be messy if I add the length of the ladder. I guess I'm gonna do it just for visual support, right? So the length of the ladder would be from around here to here. Hopefully this is parallel. All right, so this is the length of the ladder. No, it looks tacky, right? So maybe if I move it here, then I move my normal force. I know I'm making this unnecessarily long. This is the normal force. And this is 4.1 meters. So length of the ladder equals 4.1 meters. And the distance D, that one is really too long. Distance D is here, right? At the toddler. So then the force of the wall is being applied from the pivot point is 4.1 meters. So the distance from the pivot is 4.1 meters. And we have the angle at which it's applied is this over here. This is the angle over here. And hopefully you remember by geometry, these two are alternate interior angles. So this is theta as well. So then we have that torque 1 is torque 1 is the radial distance, that is L, times the force of the wall, times the sine of this angle, which is theta. There you go. That is torque 1. Distance, force, angle. Okay. And in case you forgot what the formula for torque is, I'm just going to write it down over here. This is the general formula. Torque is equal to radial distance times the force times the sine of theta. Okay? Torque and force are vectors. So now let's continue with torque 2. So then torque 2, for torque 2 we need a distance. Now, the distance from the pivot here, right, this is half of the ladder. Oh my God, I keep doing this. This is half of the ladder. So this over here is L divided by 2. Half the ladder is L divided by 2. But that's not the one I want, right? I know that the force has this direction. So from the pivot, this force, based on the plane, is acting here. I want this length over here. This length. And I know, you know, what we're going to use. We're going to draw our triangle. Super nice. There you go. So this is for torque number 2. I'm going to complete the triangle. And then my hypotenuse is half the ladder. That is L divided by 2. That's half the ladder. I know this is 90 degrees, right? Don't forget that. We're going to use that right now for the angle of the torque. And this is theta. And I want to know this distance. This is the distance I'm looking for. This over here. This is the distance from the pivot point. And I guess we can call it radial distance 2, as this is for torque 2. I have the hypotenuse adjacent, so I have to use the cosine. So the cosine of theta is equal to adjacent divided by hypotenuse. So then R2 will be L over 2 times the cosine of theta. Okay, so now I can write L divided by 2 cosine of theta. Because the force vector is directed in this direction, this is my radial, I guess, axis, right? So the force is directed here, and then you see that 90-degree angle. So in this case, it would be times the sine of 90 degrees. But we know this is 1, right? So I don't need it, truly. So I'm just going to erase it. And then for torque number 3, oh, wait, I didn't put the force. The force is the weight of the ladder. The weight of the ladder. There you go. Now for torque 3, I'm going to use the weight of the kid. And the distance is going to be very similar. Very similar to torque 2, but now I'm not using half the ladder. I'm using distance d, the maximum distance that he can climb. Or she, they, whatever. There you go. This is my other triangle. Move it over here is a little bigger, as you can see. Just place them just the same. Let me complete the triangle. It is the same thing, guys, right? It is the same thing. This is the distance d that he walks, the maximum distance. It's 2.2 meters. This is 90 degrees. This is theta, and I'm looking for R3. Based on the same situation, I'm still going to use the cosine. So I know that R3, that's kind of ugly. R3 is equal to d cosine theta. I'm using trigonometry to find these distances because the forces have this direction, and this is the distance that I want. This is L over 2 cosine theta, and this is d cosine theta over here. So now my torque 3 will have the radial distance, which is d cosine theta, times the force, which is the weight of the toddler, that is mg. Again, times the sine of 90 degrees, right? But I know this is 1, so we don't need it because we know, as I said, it is 1. Because we know this is the direction of the force, more or less. And this is 90 degrees. Okay, now we have all the torques. And as we continue with the sum of the torques, it'll be the sum of the torques. So this one, okay, so this one would do like that, negative. So we're going to make this one negative and these two positive. Now, you know what? For simplicity, I'm going to make this one positive and these two negative. You'll see why. Just for simplicity, okay? So that'll be torque 1 minus torque 2 minus torque 3 is equal to 0. So then torque 1 is equal to torque 2 plus torque number 3. Now I can substitute my equations. I am probably going to need all this space. Then that'll be L F W sine theta, that is length of the ladder times the force of the wall times the sine of theta, is equal to half the ladder cosine theta times the weight of the ladder plus torque 3, which is d cosine mg. And I'm trying to solve for the force of friction, right? Force of friction, and I know the force of friction and the force of the wall are the same. So I'm going to substitute my force of the wall with force of friction. So it'll read L, force of friction, sine of theta is equal to half the ladder cosine theta, the weight of the ladder, plus d cosine theta times mg. when I clean this up, I know should have the letters with the letters. That's okay. I know that. But I'm going to factor out the cosine, because notice the cosine is repeated here. Cosine theta, cosine theta. So I'm going to factor this out. So I'm going to use length of the ladder times the force of friction sine of theta is equal to the cosine of theta. That's ugly. The cosine of theta times L over 2 times the weight of the ladder plus dmg. Right? And now I'm going to do this just for fun. I'm going to divide. I know I could divide, since I'm solving for I guess I'm just going to solve for force of friction. I'm going to divide by sine theta. In this, you can do this two ways. So let me show you. I'm going to divide this by sine theta. I know I can divide this by L sine theta, but I'm just going to do the sine theta. Okay. And you'll see why. So this cancels, and I know that cosine over sine is cotangent, or I can write it as 1 over the tangent of theta. And since not all of you are taking pre-calculus, some of you are taking algebra 2, I'm going to keep tangent because we have been using mostly sine, cosine, tangent. So I'm going to rewrite this as 1, or this whole thing, over tangent theta. Okay, this is a trigonometric identity. Cosine theta over sine theta is either cotangent or 1 over tangent theta. So then I have length times the force of friction equals length, half the length of the ladder, the weight of the ladder, plus dmg in parentheses, divided by the tangent of theta. Now I'm trying to solve for force of friction. That is, I divide by the length. This cancels. And I divide this whole thing by the length. Right? If I do the cheeseburger method, or however you want to do it, my final equation will read like this. The force of friction is equal half the ladder times the weight of the ladder plus distance d, mass of the kit, times acceleration due to gravity, divided by, that's ugly. So let me just add parentheses here. And I will use my tools, because why not? I'll divide it. Let's fix it. I'll divide it by the, L tangent of theta. And we have all of this, right? We have the length of the ladder, weight of the ladder, dmg, and theta. All of it we have. We didn't even need the coefficient of friction. And I guess we could have added the coefficient of friction to get rid of, no, just like that. This is fine. Okay, let's not make this complicated. So then the force of friction is the length of the ladder, that is 4.1 meters. 4.1 meters divided by 2 times the weight of the ladder, which is 91 newtons, plus the distance d, maximum distance 2.2 meters, which we found in the other video. Mass of the kit 21.7, I think. Yes, 21.7. Don't get dizzy. Sorry. 21.7 kilograms times 9.8 meters per second squared. Then I'm going to use brackets because this is a lot. It's a lot of stuff. And all this will be divided by length of the ladder, which is 4.1 meters, times the tangent of theta, which is 60 degrees. 60 degrees. Tangent of 60 degrees. For the sake of time, I'm not going to solve this one on the calculator. You can do that on your own. But be careful, right? Because this is a long formula to work on. To work. And no, you know what? I'm just gonna do it for fun, just for fun, right? So we're gonna start with. I need to make this smaller so I can have my parentheses. There you go. So we'll start with 4.1 divided by 2 times 91 times, plus, plus 2.2 times 21.7 times 9.8, and all that will be divided by parentheses 4.1 times the tangent. Let me make sure I'm in degrees. Yes, I'm in degrees. Times the tangent of 60 degrees. When I did this last year, I think something around the 90s. I think. Let's make sure that is correct. Oh yeah, there you go, 90s. So we have this stuff. So it'll be 92.15, right? 92.15. So the force of friction, disregard this one. 90 what? 92.15? Yes. 92.15 newtons. This is the force that is keeping the wall from falling and the toddler from getting seriously injured. And that's it. Bye.